Hello everyone. I'll be talking about our work on photon-starved scene inference using single photon cameras, where we tackle the problem of low-light scene inference. Generally, computer vision inference models are trained and tested on images taken under sufficient light. But under low light, this becomes very challenging. This is primarily due to large amount of noise in low light images. As you can see, the scaled up image on the right is extremely noisy. This noise is mostly composed of two components: read noise from the sensor and shot noise, which is due to the stochastic nature of photon arrival on the sensor. In case of low light conditions, the number of incident photons on the sensor is very small, which makes the signal to noise ratio or SNR of the image to be very low. A new emerging sensor technology of single photon cameras or SPADs is coming up for such conditions. These sensors are capable of capturing images with minimal read noise. They can capture low bit frames at a very high frame rate. For example, this camera can capture a sequence of binary frames with up to 100K frames per second. So despite having minimal read noise, these captured frames still suffer from strong shot noise. For instance, this image on the right is a simulated binary frame captured by a single photon camera under low light conditions. Since the average PPP or photons per pixel count is very low, the image captured has a very low SNR. Our goal is to do inference on such noisy input images. But if there is no motion, we can average multiple such binary frames to get a higher SNR image. For example, this S256 image is formed by averaging 256 binary frames, which corresponds to an image taken with a long exposure. As you can see, images on the right have less noise and hence higher SNR. Our observation here is that we can generate a set of images from low to high SNR by averaging different number of low bit frames. Our key intuition is to use the spectrum of different SNR images to train robust model to do inference on noisy images. We call this spectrum of images as photon scale space. This insight is similar to the classical image scale space where different resolutions of image are used to analyze the image at different scales. We also propose a meta-training architecture to use these photon scaled images and to perform guided training where high SNR images can help learn better features for low SNR images. As you can see from the figure, we train a shared model for different levels of SNR input. We sample them in the same mini batch and use feature consistency loss on output features at different levels. It encourages features from different levels to be similar to each other. This is because even though the inputs are different at each level due to different amounts of noise, but the scene content is still the same, and hence the high level features should be similar. This ensures that the high quality features from high SNR levels can guide the features at low SNR levels. Our approach is very versatile as it can be used for a variety of computer vision tasks. We demonstrate our results on two tasks: image classification and monocular depth estimation. We use BIRDS dataset and CARS dataset for evaluating image classification using simulated noisy images as well as real captures. Simulated images under low light are shown in the second row. This table shows top 1 accuracy of image classification on both datasets. PhotonNet outperforms baselines and previous state-of-the-art for all PPP levels, details of which are presented in the paper. Following images are example images captured using SPAD camera. We get similar results on real captures where PhotonNet outperforms the baseline for all noise levels. We also show results for monocular depth estimation task where we use NYU V2 dataset. PhotonNet outperforms the baseline both qualitatively and quantitatively on all major metrics. As we can see, PhotonNet depth predictions are much clearer and have sharper edges. In future, a natural direction is to extend this idea to more computer vision tasks like object detection and face recognition. Thank you.